Hello, welcome to my channel. I've been building a 5 degree of freedom plus the end-effector robot for a while now, and as you can see on the screen, on the right side of the screen, we have a robot here. It actually has it has actually 6 servo motors, 5 of them, the 3 of them on the base frame. One of them, this one, is actually returns robot on this axis. The other one actually returns this whole link, starting from the servo 2 to the servo 6. It turns this whole link this way or this way actually, and you cannot see in this photograph, but there is another servo behind these 2 servos that actually returns this link starting from this servo 4 to the end effector. It returns this link around this axis, this way or this way actually, and we have this 5th servo motor that actually returns this end effector. It returns this end effector. Its z-axis is actually towards us or towards or inside the paper, so it returns this whole gripper up and down, and the last servo is actually opening the gripper and closing the gripper. So I've been building this robot for a couple of weeks now. I've bought it from China, and I've been using stm32 F091 stm32 F091RC microcontroller. It's a M0 series microcontroller from the STM company, and first of all I've started having just a 5-volt bus from the microcontroller to the servo motors, but that's actually very dangerous. You can damage the board. So I've got a 5-volt 26 amperes. It equates to 130 watts of power. It's a power supply that I've got. So I've been feeding the servo motors from a common V-bus line. This is a breadboard. These servo motors on stall, as you can see on the this is the so first of all let's talk about Denavit-Hartenberg tables. So to be able to control this robot, to be able to do forward kinematics with this robot, we actually need to establish a Denavit-Hartenberg table with the links, with the frames, with the location of the frames in 3D space. So I've been using I think it's called caliper to measure the parts. Measure the places where the frames are located in the robot. So to be able to compute the forward kinematics matrices. So first of all, this is the robot. It's actually not the same robot. This is actually from a website called, I was checking on YouTube. I was trying to assemble this robot that I got from China, and all of a sudden on YouTube I've seen a video from someone from Germany, I guess, and he was actually supplying this robot, and I think it looks like the same one, but I've been measuring the parts and establishing the establishing the matrices by myself for now. So I just want to make sure that if these measurements are the same or not. So let me think what I was talking about. So yeah, I've been using Eclipse as an IDE to build this robot. I have let me see, I have different joints. There is a capture compare register in stm32 PVM generation mode. I was experimenting with different capture compare values for the different servo motors. So as you can see, we have I have 3 timers. This is timer 14 it's a timer that I've not been using. So I have 3 actually MX. I've been using let me see, Cube MX. Actually, I've been using stm32 Cube MX to generate the necessary files for this robot. As you can see, I have different timers, timer 1, timer timer 2, timer. I'm also using timer 3 as well. Timer 14 is not. I was just experimenting with something in timer 14, so I'm not using it actually. And what else? So these timers, I've been generating PVMs using these timers, and actually I could write this program in a completely different way. But for example, for the base servo timer, we have a timer to use channel 1. For the end effector, we have the timer to use channel 2. For timer 3, I'm using timer 3 for the servo on my side. Actually, servo, I'm not sure if you can see on the screen. Yeah, on the right side, it's the photograph is quite big, and probably it's blocking the codes. So this is the timer 2. It's timer 3 channel 1, and this timer 1 channel 1 is the servo 4 it's this servo 1. So I have 3 servos here on the base, and this is the 4th one, the 5th one, and the 6th one. So this servo 4 is actually returning this whole link onto the left side or the right side. Its z-axis is towards this link. So timer 3 channel 1 is the servo here, this one, and timer 1 channel 1 is the servo 4. Timer 1 channel 2 is the servo that is behind the servo 2. So basically timer 1 channel 1 is this one, timer 1 channel 2 is the servo behind this one, and timer 1 channel 3 is the 5th servo, is this one. So I've been using three PVM generation modes for timer 1, two PVM generation with timer 2, and 1 PVM generation with timer 3. So I was experimenting with trace-printf function. So actually, I can actually give you the resources. Wait. I've been following this book. It's the Mastering stm32 book, and I've been in the chapter of PVM generation. So what else? As I told you, I was experimenting with different values, and the next step is gonna be writing equations to control this robot. So what I've been doing right now is I'm just measuring the distances between these frames, the places where the servos are located, to rotate the robot's joints, to move the end effector, or to move a link, or to move a joint in 3D space to a desired location, basically. So the next step is going to be establishing these distances, the locations between these frames, relative locations between these frames, and then establishing forward kinematics matrices, to locate or to move this robot in 3D space. And yeah, so this is the whole idea behind this project. So let me I think it's in the books file, robotics books, John Craig's book. So this is the first video, of course, but I just want to start with how these links, or how these matrices are being initialized. So what do we mean by this forward kinematics when it comes to the robotics? So let me start with this. I think you can see on the screen we have this is a Puma robot, and to be able to write these matrices, first we need to create the Denavit-Hartenberg table. And Denavit-Hartenberg table, it's actually all about the axis and the joints of these robots, to establish rotation matrices and the transformation matrices of these servo motors, to be able to locate the end gripper for different angles for these with these servo motors. Using these servo motors position in 3D space. We will calculate the end effector's position in 3D space as well. When it comes to inverse kinematics, we want to move the robot to a place, but we need to find out which angles are needed to move the end effector or the robot's different links or different joints in 3D space using this calculated angles. We need to go to these angles to be able to move the robot to the particular place in 3D space. So let me start with describing you about this. Let me start showing how these how do we define axes for different frames of a robot. So this is a Puma 560 robot. So as you can see, these pairs of these axes X, Y, Z. This is the base link, as you can see. So let's imagine how this robot rotates. Okay, so this motion is here in this joint. We have a revolute joint that actually returns this way or that way. So z-axis is taking to be the rotation of the robot's joint. So as you can see, since this robot returns left or right, the z-axis is taking to be upwards. And so if you imagine this robot from the left side, if z it's upwards, you can use three-finger symbol, x, y, z, x, y, z. So since z is upwards, and if you take the x to the right side of the frame, x is to the right side of the frame, z is upwards, so y is supposed to be inwards. So y-axis is inwards, z upwards. So, but for this robot, we can also see something quite different, that actually the frame 1 and the frame 2 is actually coincides in the same place. So this link's rotation is either upstairs, it's upwards or downwards. So this link's rotation is inside the paper. So the Z2 is inside the paper to the right side, because the link rotates like this. So the Z axis is actually in the direction of the rotation. So since this link 2 rotates this way or that way, the Z axis is actually coincident. I'm not sure if it's the coincident, but it's perpendicular to the link 2. So Z is inside the paper. X is, so how do we actually take the x axis? That's also a very important concept. This x axis is taking to be perpendicular to the current Z frame and the Z frame before this axis. So this is perpendicular to the Z2, but it's perpendicular to the Z1 as well. So x2 is taking to be on the right side. So, but it could also be taken to the left side as well. But the problem is, we need to be able to establish a very common, a very generally working concept that will allow us to calculate, first of all, to be able to fill out this Denavit-Hartenberg table and then calculate the forward kinematics functions. So x2 is taking to be perpendicular to the Z2, which is also perpendicular to the Z1 as well. And if we use the right hand rule, if Z2 XYZ, Z2 is inside the paper, X2 is on the right side, and Y2 is said to be downwards. So Y2 is this way. I mean, this robot, Puma 560, is quite different than the robot I've been actually building on the right side. As you can see on the right side of the photograph, on the side of the screen. In this photograph, in maybe you cannot see in the photograph, but the third servo, maybe I should use another photograph for this one. This is not clarifying my point. It's not clarifying my point. But there is actually another servo behind the servo 2. This is the base servo on the left one, which returns the robot on the left and the right axes. I mean on the left and the right side. This second servo rotates this link this way, like the one as you can see in this Puma robot, since this returns this whole link. But this servo, the third one, behind these two servos, is actually attached to this whole link via a metal. It's attached to this link via this sheet of metal, and when that servo actually rotates, it actually rotates this whole link. So since the location of the servo, I mean, even though the location of the servo motor, the third one, is behind the second one, it's actually returning the whole, it's returning this whole link. So that servo's position mathematically, or when thinking about the Denavit-Hartenberg notation, that servo is actually taken to be here, coincident with the fourth one. So the fourth one returns this way, and the third one behind the servo is actually rotating. I mean, it's actually rotating it's rotating from the other side this whole link upwards or downwards. So we will see later in a how to say, we will see later in a more detailed way. So as you can see, this is the third link. Z3 is inside the paper. The rotation of this link is this way or that way. It's like this or like that. So the Z3 is taking to be inside the axis, because Z is also is always taking to be in the rotation in the rotation. Z axis is taking to be on the rotational how to say. So Z rotates. So since this robot rotates this way or that way, Z axis is said to be taking on the with the same direction of the rotation. So Z3 is taking to be inside. X3 is taking to be taking to be perpendicular to the Z3, and also perpendicular to the one behind that as well. And X to the right, Z inside the paper, Z is inside the paper, X to the right, Y becomes a downwards, so Y3 is downwards. So in the end effector, in the gripper, we have, this is 6 degree of freedom robot. So what do we mean by the 6 degree of freedom? So first of all, our degree of freedom comes from the independency related to the motion of the end effector or the robot in 3D space. So what do we mean by that? So for the base link, we have this is the first degree of freedom, because our robot actually can return in his base frame either 360 degrees or my servos. These are really they're like toys basically. They can return 270 degrees, and these servos, for example, can return to 360, for example, when we're talking about industrial robots. And so this is the first degree of freedom. This is the second one. It can move this link. This is the third degree of freedom. But in end effector, we have row, pitch, and yaw. So what do we mean by that? So basically, we have 3 motion in the gripper. First of all, the gripper can, for example, return this way, right? It can return from this side like this. So what do we mean by that? We have this motion from upstairs. We have this motion that returns this one. And so we also have this motion from here that actually, when it rotates, it lowers or it makes the end gripper lower or upward. So we have 6 degrees of freedom. But in my robot, as you can see on the right side of the screen, 3 for the base frames, for these 3 servo motors, the 4th one, the 5th one. Okay, these are completely in line with the Puma 560 robot I've been showing you the example of. But the 6th one is actually just opening the gripper and closing the gripper. So we lack a degree of freedom there. So which one is that? If you can see which one, this servo rotates like this. This 5th one is actually helping it. So when this rotates, this 5th one is helping the end gripper to. So this 5th one, when it returns, it helps the end of gripper to go like this or like that. Okay. But what we don't have? We don't have this this different freedom of motion that helps, for example, the gripper to return like this. So we don't have, this robot doesn't have that. So it's actually 5 plus the gripper's motion. It's not 6 degrees of freedom. And so to check the place of these, so when we look at this robot from upstairs, I mean from the upper side of this robot, we can see that this is the 3rd. That's actually that's not. Yeah, it's the forearm. This is the forearm of the robot. So as you can see, this is the 3rd frame. This is inside the paper. We have Z3. Inside the paper we have Z3. So when you check from this side, Z3 is inside of paper, X3 is upstairs, and Y3 is to the right. X3 upstairs, Y3 is to the right. So basically you check like this. So Z4, Z5, so 4, 5 and 6, they are in the same place basically. You see, they're in the same place. So they are all inside of paper. Okay, so this is the 4th one. So the 4th one, this motion, I was talking to you about this, the 4th servo motor that I've been, the 4th servo motor. So this 4th servo motor is helping this link to return this way or that way. Yeah. So this 4th one is as well the same. It's a coincidence basically, but this 4th one is Z is this direction. So it returns this forearm this way or that way, and X4 is perpendicular to the Z4, but it's also perpendicular to Z3 as well, because Z3 here is inside the paper. So this X4 is perpendicular to Z3 as well. So for the 5th one, Z3 is inside of paper. So what do we mean by that? Z3 is inside of paper. So here inside of paper, we have a motion that is actually returns like this motion. The first one was returning this like this. This 5th one is this. What about the 6th one, which I lack of in my robot? 6th one is actually Z6 is to the Z6 to the right side. This is the end-effector. This is the end-effector's frame. The Z6 is actually on to the right side. As you can see, this is the place of the end-effector. So it returns the whole 4 and 5 link, which I don't have in my robot. This is the 4 and the 5. So I should have had another servo motor that actually returns this whole. What's happened? Okay, I'm not sure. I've been using OBS Studio for the first time actually. So I should have had another servo motor that actually returns this gripper. So for example, this robot went to a place in 3D space and stayed there, and this whole link that had been holding this and effector should have had returned, but it doesn't. So so that's the whole point. I'm sorry for my English. I've been trying to explain you everything in detail, but my English may not be enough to explain you everything. But during the development of this robotic arm, you and me, we are both as well, establish a relationship between each other that will actually clarify all of the problems related to this robot. And so I showed you the example from a Puma 560 robot. So let me see the Denavit-Hartenberg table. So when it comes to Denavit-Hartenberg tables, we have some parameters. We have different links, link 1, link 2, link 3, link 4, link 5, and link 6. So we have the I, the theta I, alpha I minus 1, a I minus 1. So what are these? So these are basically parameters. These are basically everything that governs our everything that governs or everything that limits our robot's functionality. So basically we can see that so we have AI, alpha I, DI, theta I. So what are these? So theta I, the angle, this is the, so how do I describe these angles? Is that this this theta I is to rotate the robot in z axis to make the x-axis in line with each other. This is what theta is defined. So how we define theta is the rotation along z-axis to match the x-axis in 3D space. So in contrast with theta I, alpha I is the angle. So it's the angle of rotation around xi. The other one was in zi. The angle of rotation around xi to match the z's, to basically match the zi's. So to match the zi and zi plus 1. So AI and DI. So AI is not artificial intelligence in this context. AI here is the distance between frame zi and zi plus 1. So the distance along x between the consecutive z frames. So this xi, the distance between z frames measured along x-axis. So di is the distance measured along z-axis. No, distance measured along z-axis between the consecutive x frames. Consecutive frames and their x-axes. Okay. What else? So now we can actually check how these values come from, where these values come from. So the first link, this one, the first frame and the first joint, rotation is either this way or that way. So we have the theta I, which is theta 1 angle here. This is a variable. When we move this robot along around this theta I, the robot's end effector, or every joint of this robot, will move with the motion of this joint. So let's look at the second frame is here. We have a distance between this the first frame and it's here inside the paper. So as you can see, since frame 1 and frame 2 are coincident, they are in the same location. We don't have any distance between the first one and the second one. So the I and AI are zeros. You see? So theta I is theta 2, which is the variable, which is the servo motors. In my case, in this stm32's PVR generation mode, the capture compare register value is theta here. So let me see. So Z2 here in the second frame is inside the paper, and it returns this whole link. And So let me check the so from where this I minus 1 come from. So this is to rotate the x to match the z's, yeah? So what was a? To rotate the x to match the z's. The definition was somewhere here. I'm not actually, oh, where we're gone. It's in kinematics. Where is it? It's inverse kinematics. We need to check the forward one. Yeah, it's here. And what else? So AI, as you can see, measured along xi. This is the distance. Alpha I, measured about xi. This is the degrees. So to match the z's, basically, to match the z's, how do we return the x-axis? So let me see. So in the first one, x1 is here, and the second one, x2 is there. So to match the z's, we need to rotate the x to match the z's. So how do we return? When you check from this side of paper, I'm not sure if I can actually show this. Is there any? Let me see. Right, draw, LibreOffice draw. So let me see. Tools. Show glue points. I've been not using this for a while now. Okay, so in this frame, if you look from this side, is it recording? Yeah, it is recording. If you check from this side, y1 is to the right and z1 is upwards. So how do you, y1, this is y1. Insert the text box here. This is y1. This one. But please consider this as a vector. This is a vector basically. Y1 is on the right side. Z1 is upwards. We could make a vector as well. Let's make a vector then. So what is this? This is it's F2 here. This is Z1. Let's make this a vector as well. It's Y1. So when you check from this side, X1 is towards us, Y1 is to the right, and Z1 is to upwards. When you check for the second frame, so we return the X to match the Z's, yeah? So in this second frame, ZY is this way. This is Z. This is gonna be Z2 to the right side. Y2 is downwards. Okay, it's not. Okay, this is Y2. So what happens is that, so we need to return this X1 to make the Z's in line with each other. So what do you do basically? You have a return this way. You need to return this way. So what happens is that when you return this whole frame 90 degrees, Z1 and Z2 becomes in line with each other, and Y1 and Y2 in line becomes coincident with each other. So you make a return or rotation in the clockwise direction. So the rotations along in the rotations along the clockwise directions are minus rotations. but the rotations in the counterclockwise direction is a positive rotation. So while filling out the Denavit-Hartenberg tables. So here, then this is going to be minus 90. Yeah, minus 90. So the third one and the third frame and the second frame. This is the third one. This is the second one. Third one, we don't have any. We don't have any. As you can see, the third one, the second one, the axes are basically the same. Z's are looking at the same direction, x's as well, y's as well. So, but what do we have? So we have, of course, we have the theta 3, which returns this third frame here, since Z3 is also inside the paper. And so we have A2 and D3. So what are these? So now we need to be concerned about what are A2 and D3. So the I is in the Z direction, the distance between axes. So as you can see, D3, so this is the Z3 is inside the paper and Z4 is here. No, it's between these, Z2 and Z3. Let's look at AI again. No, DI. Distance between the X frames measured along ZI. So measured along Z3, measured along Z3, measured along Z3, distance between X2 and X3. As you can see, so along Z3, distance between X2 and X3. So X2 is here, X3 is over here, measured along Z3, distance between this point and this point. So this is the distance between X2 and X3 along Z3. Along Z3, X2 and X3. You see? X2 is this way, X3 is this way. Along Z3, the distance is this frame. So this is A3. So we write, it's supposed to be A2. Wait a minute. Measured along Z3. This is the A2. Wait a minute. Is that D3? Yeah, D3 is actually, it's here. Okay, D3. Measured along Z3 between X2 and X3. D3. Okay. I'm just confused for a while. The other one is along X I minus 1. Distance along X. So between the Z frames along X. So along X3, between Z2 is here and Z3. So this is A2. Let's look at the fourth one. It's here. Z is inside the paper. So the distance along Z4, the distance between X3 and X4 is D4. It's supposed to be D4 here. Along X, the difference between Z, along X, between the difference between Z, along X4, between Z4 and, between Z3 and Z4 is A3. It's here. To match the rotation along x to match the z's. Rotation along x to match the z's between 4 and 3. So where is 3? Here. The 4th is here. So let's see. This is 4, by the way. But we need to draw the 3 as well. 3 is here. Okay. So z is inside the paper. You remember that. So new page. We have two vectors. This is the x3 is upwards, and we have another vector which is this way. I think I need a graphic tablet, but I'm not sure. I think this is gonna be okay. So these are actually perpendicular. This is y3, this is x3. So let me insert the text box here. This is gonna be y3, and the text box here, this is gonna be x3. So the 4 and the 4 one, x4 is upwards. This is x4. This is z4. So we need to what we were checking out here, yeah. So to match the rotation along x to match the z's. So I forgot to put x, y, z. X is upstairs, y is this way, z is x, y, z. X is upstairs, I mean upwards, y is this way, so z should be x, y, z. Y is like this, x is like this, z is inside the paper, so it's like this. This is z3. Why this is so z3. And in the other one, x, y, z, z is, as you can see on the right side, z is like this, x is upwards, x, y, z, x is, and y4 is inside the paper, x, y, z. I'm just trying to make sure that it's correct. Z is this way, x is upwards, y is inside. So this is y4. So we need a rotation along x to match the z's, right? Rotation along x to match the z's. Z is inside here. So we will make a rotation and it's gonna match the z. So when you, by the way, I think this is not correct. X, Y, Z. X, Y, Z. Z. Yeah, that's correct. And the other one, X, Y, Z. X is upwards. Y is here, and Z is. The only difference is, I think, Y is this way, and X, Y, Z. X, Y, and Z. So actually, yeah, that's not wrong. X, Z is inside. Yeah, that's correct. So there's gonna be a return along x3 to match the z. So this is a rotation in the clockwise direction. Z3 is gonna be here, and y3 is gonna be on our side. So if you see this, Z3 is inside of paper. So but rotation along x. So when you return along x. So you see, yeah. So when you return along the z in the clockwise direction, I'm just rotation along x to match the z's. X to match to along x around x to match the z's. So around x to match the z's, basically around x, not around x minus I, around xi. So yeah, that's the whole problem. The problem, so to rotate around this to match the z's. So we will rotate this one to match the z. So this is going to be returned on the counterclockwise direction. So that's supposed to be, no, between 3 and 4, yeah? Yeah, that's, I've been using this one. Between 4 and 3. X4 and X3. Yeah, I was checking for the wrong one. This and this one. So rotation along X to match the Z's, yeah? So Y is inside the paper here. So we will return this X to match the Z's. So this is going to be returned. So we will return like this direction. Maybe I'm just rotation along rotation minus or positive in robotics. Let's see here. This is the clockwise. No, that's not relevant. So x3, y3. So we need to rotation along x to match the z's. So in this one, z is inside the paper. In this one, z is here on the right side. So basically, we need to return this one on clockwise direction. So Z3 is going to be this side. So it's a minus 90 degrees of direction return. Between 5 and 4, this is between 5 and 4. Z is inside the paper in the fifth one. In the fourth one, Z is here. So if you check from this side, from Z4, rotation along X, along Z. Along X to match the Z's. We are, by the way, we are this one. We are in this one. Rotation along X to match the Z's. So Z is this way inside. You need to return clockwise. Wait a minute. Yeah, so between the fourth and the fifth one, we need to, so axes are in the same, so axes are in the same direction. So we don't have any rotation along Z to match the axis. So measured about Z to match the axis. So we just have along X to match the Z's. So along X to match the Z's. It's going to be I'm just trying to realize from this side, if you check from this side, Y5 is this way, Z5 is upwards. In the fourth one, Z4 is on the right side, Y4 is inside the paper. So you need to rotate this to match this Z and this Z. It can be either along Zi and Zi plus 1. So when we were checking for Z3, we should have checked this one and this one, Z3 and Z4, and for Z4 and Z5, for Z5 and Z6. So we are now checking this one, and we should check with these one. We should compare with these ones. So I made a mistake over there. So Z5 is inside the paper. In here Z6 is towards us. So we need to return this X5 to make this Z5 for this Y5, and Y5 is going to be so we'll return which direction? It's counterclockwise around X. It matches the Y's. Z was here, but now it's but that's not in the same direction. Let me check. So this is basically the whole point of figuring out the Denavit-Hartenberg tables. I will not go further because it gets complicated, and I'm not sure what is the mistake I made over there to fill the table. So yeah, in the next video I will come with a more detailed way of explaining this Denavit-Hartenberg tables and making sure that my robot is actually configured in a proper way. And yeah, the next video will be more detail, will be more in detail. So thank you for watching my video, and see you next time. Bye.